Okay, good afternoon everybody. Out there is having a wonderful day. So today I'm going to be talking about the remainder of our discussion for Prim's algorithm and the minimum spanning tree problem. Then after that I'll be talking about the single source shortest path problem. So this is a generalization of the problem I talked about briefly about computing a shortest ST path. But now I want to consider weighted graphs. So we'll be talking about that after we finish talking about Prim's algorithm, okay? So first, I want to remind you where we were with Prim's algorithm. So last day I wrote out the pseudocode. I wrote it a little bit more, with a little bit smaller of lettering here, so everything's in one spot here. So here's Prim's algorithm. So I want to remind you of the main parts of Prim's algorithm. The first thing is setting up the initial D values and these parent or predecessor values. I initially set them up, and as the graph gets explored, or in our case, as I explained it the other day, a blob devours the graph by consuming and introducing parts of the vertices into this blob, which in theory is actually just a set of vertices that for which we look at the least weight edges that cross a cut from the vertices I've considered so far that are in the blob, a set of vertices, from those that are outside the blob. So I always try to identify a least weight edge that crosses the cut that forms these two sets of vertices. And all I want to do is I want to guide the blob in a way that makes sense for a blob to do it. Remember, the blob is particularly lazy. Well, it's not even really lazy. It just kind of engulfs things that are closest to itself, right? And that is always by selecting a least weight edge. So remember, I have the setup here. Then I go through each one of the vertices, one after the other, and I determine which vertex is closest among all the D values. So I pick the one with the smallest D value, right? So I scan through all the vertices, I figure out which ones are not in the blob yet, and I just simply say, okay, well, does it have a smaller value for my D min? So once I've picked this, I've determined which vertex the blob is going to devour, and then I update what the blob can see from the perspective of the blob, which is among all the vertices that are in the blob. Can I discover anything new? Now, you'll notice very quickly that the only things I have to update are what I discover once the blob devours that vertex. So when I devour, well, not I, the blob devours, sorry, I'm just having a lot of fun with this. When the blob devours U min here, the only part I have to update for my D values and parent values are all of the endpoints of edges that are incident to U min. So that's what this loop here is accomplishing. So all I do is I'm just exploring the graph as I reveal more of the graph through my actions as the blob. I'm just going to explore this and I'll update those D and parent values appropriately. Now, one thing I mentioned the other day is I kind of wrote it out so that it doesn't return anything. A remark I wanted to make was that Prim is very easy to modify to return all sorts of things. So for example, if I want to return a set of edges instead, one thing I want to point out to you is that if U min its parent is not null, then I can determine what the least weight edge I picked actually at this point in the algorithm. So you notice where I marked U min here? That's exactly when you know what the least weight edge that gets selected is. So for example, if you want to modify prims so that when you start this thing off, you create, say, a list or a set, and what you do is you have it where every single time you want to introduce another least weight edge, you perform this operation right here. So you just do the insertion of the edge right there into your collection or container. And then you can just simply return it after this main for loop. So that's one way you can modify Prim's algorithm to achieve this. So hopefully that's clear to everybody why. Remember, every time I look at whatever is from in the blob to outside the blob, and to determine the parent is determined whenever as I explore, well, the blob explores the graph. Okay? So I want to do an example with you, then we'll do the time complexity analysis. So as I mentioned last day, I'm going to go a little bit faster over this because I asked you to take a quick peek at this. So I'm going to consider this example graph. Oh yeah, let me put these edge weights on here. That's one part I'm missing here. Let's put the edge weights on. 2, 4, 2, and 1. There we go. So I'm going to imagine that the blob, which remember in the cut property, the blob is V1 once it consumes the start vertex. So just remember, the underlying property here is that we're using the cut property to ensure that we end up with a minimum spanning tree at the end of this process, because we always select an edge that belongs to some minimum spanning tree. So I start off at vertex 3. So what happens? Well, let me get a different color here. Let's use blue. So imagine I start there and then I set the D value for S to be 0, and its parent is currently null. I wrote it as nil. I use them as synonyms here. So what happens in this first iteration? Well, it will select S, because S is the only one that doesn't have infinity as its D value, right? So that means that the blob is going to consume, it consumes 3. 3 is a part of the blob now. So now what I need to do is I have to go through all of the edges incident on 3. So I have to go through each one of the edges that are incident on it, look at their opposing endpoint, and see if I can improve their D values. And also, of course, update their parent. So I'm going to go through each one of these incident edges. So I just simply say, okay, well, is this weight better than infinity? And the answer naturally is yes. So I'm going to update infinity here to be 3, and its parent is 3, because this is the edge I would use if I were to pick this edge and included that as a part of the minimum spanning tree. Now, I don't know if it is yet or not. We will find out. And of course, I update this one because that beats infinity. And of course, 2 beats infinity as well. Let me update the parents here. So these should be 3. And that's 3 as well. So now I've performed one iteration of this larger for loop. So remember, each time, the easiest way to remember this is the blob always selects the least weight edge that goes from one side of the cut, i.e. the blob, to outside the cut. All the other vertices that the blob has yet to devour. So, the question is, which one would the blob go towards? Which one? Which one's the first one? Which one should the blob go towards if we're following prims here? So remember, the next iteration, it will select the vertex with the smallest D value, right? But which one is that? Which one is it? Yeah, it's vertex 4, right? So we know right away that that's going to be what the blob is going to devour. The blob devours vertex 4. Now, if you're wondering what the least weight edge I picked is, it's this one right here. As per what I said here. Then I go through all my incident edges. I go through each one of them, and I see if I can improve its D value here. So, what I need to do now is I just simply go through each one, and I say, hey, okay, well, let's see. Well, notice here that 1 is in fact less than 3, so I better update this D value to 1. And its parent now is 4. And, well, naturally, the D value was the same one that got me here. So you know that this one isn't going to get updated, right? I already got there, and regardless, it's already in the blob. It will not get selected. It will not select vertex 3 again. So notice that as I do this, one key thing I want you to notice is the blob is never going to pick an edge that creates a cycle. The reason why this is guaranteed is because I always pick edges that go from inside the blob to outside the blob, not within the blob itself. And this assures me that I'm not going to get a cycle. So it's one thing I want you to notice. So, naturally, let's keep going. So let's see. We got ourselves, out of our values here, we have one with 1, we got infinity, and we got a 4. Which vertex is the blob going to devour next, everybody? Which one? Which one is the blob going to devour? Don't make me start singing. Okay, so here we go. It entertains the blob, by the way. I'm just entertaining the blob. So we know vertex 1 is what goes in next. This is the least weight edge that gets used because its parent was 4. And then naturally I go through all of my incident edges and I see if I can update any D values and their parents. So very nicely, notice that I can get to this vertex now. So I update its D value to 3, and like I said, its parent to be 1. And, well, notice I can't improve any of the other ones. In fact, I would not touch them, right? Because this one most certainly wouldn't get me there because, like, the D value is already 0, right? There's nothing I'm going to do to improve upon that. And this is the edge that I used to get to this vertex in the first place, right? So, the key thing I want you to notice is I always select the least weight edge that goes from inside the blob to outside the blob. The other thing is when I do these updates, it's always from the edges that are incident on the vertex I've selected that goes inside the blob. So, next, which vertex does it pick next? Which one is going in the blob next? Yeah, vertex 2, right? So let's put vertex 2 in. Vertex 2 is going in the blob. Why? Because this D value is 3 versus 4 here. And this would be the least weight edge I select. Because its parent is 1. And naturally, if I were to keep doing this, and notice I could check all my incident edges. Notice that I have a 2 here I could use that's better than the 4. So I'm going to update its parent and the D value. So I pick 2, and its parent is 2. And finally, the blob will select vertex 5. And the blob has devoured the entire graph. So notice that when I pick this one right here, this would be the least weight edge that gets used. So, once I complete this process, notice that I have now a spanning tree because it has all the vertices, and that's because the blob devoured every vertex. Likewise, because of the cut property, the edges I've highlighted here in blue constitute the minimum spanning tree. So that's the conclusion of me applying Prim's algorithm. So are there any questions about what we just did here in this example? Are there any questions at all before we proceed to the time complexity analysis? So don't be shy. So one thing I will acknowledge that the start vertex, if I pick a different start vertex, I may get a different minimum spanning tree. But I must stress that that's highly dependent on what I said the other day, where I said that it's possible for there to be multiple optimal solutions. Sometimes you'll get the same exact tree, in certain conditions. For example, if all of the edge weights are distinct among all the edges, there's always going to be one minimum spanning tree. However, if there's duplicates, for example, it may not necessarily be the case. But that's just something I thought I would bring up. But other than that, one thing I'll also point out is that some variants of Prim's algorithm, you'll notice in our algorithm I give a start or source vertex. Some people like to make it so that you arbitrarily select the source at the beginning. But I like to keep it simple like this, so that we know exactly what we're trying to do here. Okay? So if we're okay with, or is everybody okay with this example before we proceed to the time complexity analysis? Give me 2 thumbs up if we're all good with this. Wonderful, wonderful. So next, let's go to the time complexity analysis. I'm going to kind of whip through this like a boss. I don't know, I'm just having a lot of fun here today. As soon as I start seeing graphs, I get very excited here. So I'm going to go through this. So remember, n is the number of vertices and m is the number of edges. So just keep that in mind. So at the beginning, I start by going through each vertex in the graph, right? So you know right away, this part, since these take a constant number of operations to do, this is big O of n, right? This is some constant number of operations. I'll just call it C1. And now I have this nested loop. In fact, there's a loop with two nested loops inside it. Now, I alluded to this the other day, that very often you're used to having it where, okay, there's some number of iterations that happen here, and then there's some number of iterations that happen here, and naturally what we do is we multiply the numbers of how many occur in each one together, right? It's very often how we count operations with nested loops, for example, or at least that's how it plays out. I like showing this example because it absolutely breaks this intuition if you want to do it carefully. So I like to show this just to introduce you to this. So the first thing you know right away is that this outermost loop performs n iterations, right? It performs n of them. So you know whatever's happening in here, it's going to be whatever's going on in here for the total number of operations times n, right? We know that. So, you know this loop right here. For each vertex u of G, we do stuff. Well, I'm just going to lump the marking of this. D-min and U-min being assigned to null. I'm going to just take all of this. I'm just going to throw it all together and say that that takes big O of n. Just for the sake of time, otherwise I would introduce a constant for it. This is just for the sake of brevity here. Now next, there's this right here. For each edge that's incident on the vertex U-min, we do the following, right? We go through and we update the d value in the parent if we find a case where we can improve upon it. Now, all of this that's happening inside this loop is some constant number of operations, correct? Because I have access to all of those. However, there's a wrinkle in this process. There's something going on right here that's a little bit odd. So one thing I want to point out is that this relates to the incident edges, right? So the computation of the incident edges. So whatever it takes to compute the incident edges determines that loop right there. Because remember, I have to go through all the incident edges, right? So you know whatever comes out of this will be multiplied by n to get the computations or how many operations happen over the entire nested loop that contains multiple inside loops or inner loops. So the question is, what's going on here? And naturally, I have to talk about representations of the graphs. So the first one is talking about an adjacency matrix. So let's talk about the adjacency matrix first. So let's talk about this from the context of an adjacency matrix first. So you know right away, remember we talked about this, when I go through all the incident edges, what's the time complexity of computing the incident edges? So if I want to go through each incident edge, what does that correspond to? So how many operations in terms of big O? Or even big theta in the worst case? So how many operations are going to happen there? So think about it. So remember, we talked about this when we were looking at so we're not quite so I'm just looking at just the innermost loop part. I haven't yet incorporated everything yet. But most certainly you're going to end up with something that looks quadratic if doing this computation of the incident edges where I go through each one takes linear time, right? So you know it's going to be something that's in an adjacency matrix. It's going to be that, oh, the incident edges, that takes big O of n to compute. So it means that if you compare this, you're going to have big O of n plus big O of n, where all of it's going to get multiplied by additional n. So you end up with something that's big O of n plus some constant plus big O of n squared. So you know at the end of this process, you're going to end up with big O of n squared for an adjacency matrix. However, this gets a little bit odd. And this is quite similar to what we were doing when we were exploring the graphs of our graph traversal algorithms. Let's consider an adjacency list. So in an adjacency list, remember when I compute the incident edges, is it big O of n for the incident edges at a given vertex? What is it? What is it? Is it big O of n or is it something else? I'm just trying to contain my excitement here. And I made some weird noise just there a moment ago. But what is it? What's going on with the incident edges for an adjacency list? Remember, in an adjacency matrix, I go through each one of the columns of a given row, and that's where I got the big O of n from. What happens with an adjacency list? What's the big O for computing the incident edges? If I want to get each incident edge, and I want to perform what's happening inside of this loop here. So I will tell you up front, it's not big O of n. Well, the mayonnaise, it most certainly is big O of n, but I'm talking about big theta. What would it be, big theta? Remember there's this thing I called, it starts with a D? What is it? So remember, it's a degree. It's the degree, because remember, in an adjacency list, I go through the list of incident edges. Well, I go through each one of my other opposing endpoints, right? In the adjacency list. But what's that? That is the big O of the degree of the vertex. So if this is U min here, this is actually going to be big O of the degree of U min. So this is where it gets a little bit funky. Now the number of iterations now depends on the degree of a vertex. But now this is the big but here. This is where we have to be a bit more careful. Notice that I go through, so notice that it just says n iterations here, right? It just says n, right? There's n iterations of this. But that means, remember, I never go to another vertex. I don't revisit another vertex again, right? It goes in the blob and then I consider another vertex, right? I do this for each one of the vertices. So you know U min is going to be considering each one of the vertices at some point for each iteration of this main for loop, right? So where it looks like it's just n iterations, this n here is going to go through each one of the vertices. So this outermost for loop goes through each vertex, actually. It's just cloaked in disguise to say, okay, just do it n times. So when I look at this, it's really that I'm looking at the sum of all of the degrees of the vertices if I incorporate this with the outermost for loop. But if you do that, I want you to kind of put this all together then. So let's think about it. You know you're going to have some linear number of operations that happen up here, right? So you know it's going to have something that's like roughly n plus some constant. I'm just going to throw that all together into the n here. Then I have this loop here. Well, this happens, and this is big O of n, but I do it n times, so you know that's going to be something that's going to be like n squared, right? Now, of course, I would incorporate the constants here, but I'm just trying to be fairly quick with you here. So now, what's happening with this loop here in relation to the outermost loop here? Well, I'm going through each one of the vertices. Could somebody tell me what that is in terms of big O? Yeah, exactly. Exactly. It's big O of m. Not, so it's going to be based on the number of edges because of the handshaking lemma. Remember that cute thing I keep bringing up, this handshaking lemma? It's very useful. So when I go over all the vertices, I sum the degrees up. It's actually 2 times the number of edges, which that's big O of m, right? So I'm going to end up with something that looks like this, which this is big O of n squared, right? Because m is big O of n squared as well. This is because the maximum number of edges a graph can have in the context of our problem, because these graphs are simple, is they have no more than n big O of n squared many edges in them. We talked about this when we're talking about complete graphs, for example. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different reasons. So in both cases, I end up with big O of n squared, but for different So isn't that interesting? So we can end up with big O of n squared for these different representations, but it comes about for two different reasons, right? So I have something that's like n, then I have n squared, then I have an m. Now, I would like to make this, I want to think about this. So I don't really see any way that's very natural for me to, at least at the time of all the things we've discussed, to really improve upon this one, right? In the worst case. Because notice that to do this takes linear number of operations and I do n iterations. It makes sense to be quadratic, right? But it seems like I'm being a little bit, I don't know the best way I could describe it, a little naive here. If you actually look at this algorithm a little bit more carefully, you'll notice that I actually just do a linear scan through all the vertices here, and I just find the one with the smallest d value, right? Now, this is where the fun of things that we've talked about in this course come together. So I've shown you that we can represent graphs in a couple different ways. What I want to do is I want to see if I can improve the time complexity of the algorithm for sparse graphs, graphs that don't have as many edges in them. And naturally, when you think about that, it's very natural to think about the adjacency list representation. So what I would like to do is I'm going to see if I can improve something about Prim's algorithm for an adjacency list. So the first thing I want to point out is that regardless of what I do in here, every time I have to do this linear scan through all of the vertices right here to figure out what U-min is, right? I have to do that every single time, each iteration. That seems like a bottleneck if you actually look at the performance of this algorithm. So notice that I do this initial setup, but I'm basically doing something like this each iteration. But maybe there's a better way. There has to be a better way to do this. So that's where I'm going to be bringing in all of our friends from earlier in the course. So let's head over here and let's talk about what we could do to beef up Prim's algorithm. So this is what I want to really use this to really explain a lot of the main ideas we've seen into this course so far. Is that we've seen that we can take different representations, different data structures to represent and solve problems. But also I can try to improve upon them by realizing the drawbacks in the algorithms. So anyways, the one thing I want to point out for you, just before I get too into this, because I haven't talked about correctness yet, is that notice that every single time I perform Prim's algorithm's main for loop, I consider n vertices, but notice that I always include n-1 edges. That's because of the property I mentioned earlier, where I said that, oh, every time I pick an edge, that's when umin.parent is not null, right? So I can tell you that's not the first iteration of the loop, but that's all the other iterations. That's exactly n-1 iterations of that loop. So that's how you know it's producing, in fact, a tree. And it won't have any cycles because of what I described earlier about how we use the cut property. So the next thing is the proof of correctness. I have the proof that's going to be in the notes. I'm going to ask you to read it. It uses the cut property. It's a really slick proof that I placed there for you. I like showing it to students so that they can get an idea of how you can use proof via contradiction in the context of an optimization problem. I'll show you an example like this later on in the course. But I wanted to show you just an example of how you can use it in contrast to something like mathematical induction, which you can recast the same kind of proof in that way too. So I thought I would show you that. So this proof uses the cut property that I showed you last class. That's actually where you get the correctness from, as I suggested earlier. So what I would like to do is I'm going to try to use a priority queue to speed up prims. So I'm going to use a binary heap. So I'm going to use some heap-based implementation. And I want to address this bottleneck of computing dmin and umin for the adjacency list representation. Why? Because remember, in the algorithm, I always have to go through all the vertices. Well, it doesn't seem very, if you think about it, it's not really, like it works, but there's got to be a better way. Think of it like a TV infomercial where somebody's like, there has to be a better way to do this. And that is exactly what we're trying to accomplish here. So what I'm going to do is I'm going to use a priority queue that's implemented as a min heap. And I'm going to actually augment the priority queue to introduce a new operation, just specifically for a heap. So this operation is called decrease key. It takes in some value, which in our case, the v is a vertex, and k prime, which is going to be a new key. So it's going to be a new value for a key that has this value. So I look at the entries in my heap, and I want to know, okay, if there's one with this value v, or vertex v, I want to be able to update its key from whatever it is. Suppose it's k. I want to change it from k to k prime. That's what it does. And the idea here is that k prime is a smaller number than k is. So all we're going to do is it's just going to decrease the key of entry, that pair there with the key and a value. And we're just going to change it, just k to k prime. Now you might ask, Dan, how exactly does this algorithm play out? It's really simple, but it relies me to actually augment the data structure I showed you earlier on in the course. You know, where I have my nice classic array-based implementation? What I'm going to do, there's a couple different ways I can approach this. So the first way, now I must stress this still works regardless if you choose to use an array or a literal tree. But here's the idea. There's a couple different ways to do this. The first one is to store a positional array, POS. I just call it POS. You can call it whatever you like. That keeps track of the positions of entries. Sorry, I'm getting very excited here. Entries in the heap where each position is indexed. So here's the idea. You have your heap as an array. Each one of the positions has some key / priority and some value that's associated with that element. And the idea is that I would like to maintain a separate array. It's called POS, and it's going to be the indices of the vertices, starting from 0 up to n-1. And each index tells me its position inside that array for the heap. So it tells me where in the heap it is. So that if all I have to do is I can just index into this array to tell me what position in the heap, which is also an array, that tells me where it is. So if I need to update its key, I know exactly where it is. So you might say, Dan, that's kind of like cheating because we're kind of like ripping inside the data structure and we're making some mutations. That's exactly what decrease key actually does. It goes right inside the priority queue and says, hey, look, do you see this element here? Now it's going to have a new priority. I'm going to update its priority, and now I want you to update the priority queue. That's all it's doing. So you might ask, okay, so you can use an additional array to store this, and the whole idea is that we're going to update this array every time you mutate the heap. So when you do bubble up, bubble down, whenever you do removals and insertions, just generally, you have to make sure you update this positional array POS. So you just maintain it in the most obvious way possible. So whenever you make a change in a position, make sure you update it in the array POS as well. Now the other way, this is one that's very slick if you're storing these as actual objects, like vertex objects. All you do is you just store another attribute that tells you the position inside of the heap. That's all you do. So you just add another attribute to your object. Now, in that way, some people will tell you, oh yeah, and you're coupling the vertex object now with the with the priority queue. Yes, but at the same time, it keeps things simpler as well if you actually have these objects. So for those that are kind of software engineering buffs in the class, I assure you, I'm not trying to encourage you to use heavy-duty coupling in your code, but you could do it this way if you like. But if you want to avoid doing this, just use the array approach. But either way, it works. So these are a couple of ways you can get that so you can have this manipulation of the priority queue. And here's the algorithm. This is all you do. You update the key of whatever value it is, you index into this array, or since you have access to the vertex, which you could just simply get from V itself, that is the vertex, then you just get its key, and you can just update it to be K prime. And since it's always going to be smaller or the same, you just call bubble up. So I have a question for you. If all I'm doing is just modifying an element, which I have direct access to because of this array, for example, and I just do bubble up, what's the worst case time complexity of bubble up if there's n vertices in the graph? So does anybody have any ideas what the worst case time complexity of decreased key would be then? Yeah, it's just log n. It's big O of log n, or big theta log n. I'll just write big O of log n, so it takes big O of log n time. So the running time is entirely dependent on bubble up, by the way. So Now that I have this operation, I'm going to go back over to my Prim's algorithm, and I'm just going to incorporate a priority queue now, and let's see what happens, okay? So I'm just going to head back over this way. And let's modify Prim's algorithm so that it uses a heap instead. So the first thing I should point out is that this first loop with the setup, it doesn't change at all. And now instead of me having this main for loop, I'm going to make a couple small changes here. So I'm just going to rewrite this larger loop just for the sake of time. Much of this algorithm will not change. It's just that I have to do a couple small things. So the first thing here is I have to initialize a priority queue. So I'm just going to so after I've set up the initial D value of S to be 0, all I'm going to do now is I'm going to let priority queue Q contain all the vertices of the graph where each entry is v.d and v. So the d values are going to correspond to the keys for the priority queue. So the priority is going to be dictated by the key, and that key is d. So, which makes sense in our algorithm because we always pick the one with the smallest d value, right? So you might say, Dan, this line sure likes to suppress a lot of details, and the answer, of course, is yes. Because notice I create an empty priority queue, and then I insert all of the nodes into, all of our vertices into it. So I build this data structure. You know right away that this operation, just before I get too ahead of myself, if we're thinking about this, I do n insertions into the priority queue for this step, right? So you know right away that whatever is going to happen, you know that this operation is going to be big O of n log n, right? Because I do n insertions into an empty priority queue initially, and that's what this step is just saying me to do. Just create an empty priority queue, then I just dump all the vertices in, where I set each one of their keys to be v.d for vertex v. So I just go through each one, I create an element, I dump these all into the priority queue. So, now, let's do this. So while the queue is not empty, so while the priority queue Q is not empty, we're going to do the following. So notice I'm going to replace our big for loop with a while loop. This was actually one thing that will simplify down the algorithm a bit, so I don't have to mark the vertices, for example. Because notice if I dump all the vertices into this priority queue, all I'm going to do is I'm going to pull out elements from this priority queue that tell me the vertices that the blob would devour in the order they should be coming out. Because of the fact that each one of the priorities is, in fact, the D value, right? Which is equivalent to me going through that for loop and selecting out the umin each time, right? So all I have to do now is I just simply go umin. So I'm just going to assign umin to be q.removemin. So I just use my remove min operation, and this will pull umin into the cloud or blob. So this will put it, so this, it puts umin into the blob, right? So this step explicitly will be able to achieve this. So this is the step that's going to put umin into the blob, because I've selected it. So I must stress that you can always mark the vertex if you like, but it's completely optional at this stage, because I'm never going to use another vertex like this, because it won't be in the priority queue anymore, right? I've removed it. So I can mark it, but this is not needed. And now I'm just going to do the same thing I had before with one small modification for each umin v. So I'm going to go through all the incident edges of umin. And I'm just going to see if I have a better d value I can improve upon. if the weight of u min v is less than v dot d, then we update its d value to be the weight of that edge. We update it to be the weight of that edge. U min v. And update its parent, right? But before I do that, I'm just going to make sure I remember to decrease the key for that given one. So I'm going to go decrease key for v. And I'm going to change its key to be v dot d because I've just updated it. So this will ensure that the priority queue the next time, if the d value becomes for one of these better than what's currently sitting at the best spot in the priority queue, the one with the smallest d value, this will eventually beat it out if there's a smaller d value. That's what decrease key is here for, is to update the keys of all of the entries in my priority queue. So for each one of these, I'm going to update its parent. v.parent is going to be u min. And that closes off the if statement. That closes off the for each loop. And that closes off the while loop. So I made this small modification to the algorithm. The ideas are all the same. Just now the difference is I've taken out that for loop, right? This first for loop's gone, right? It's gone here inside the nested loop. Now I just have this for each loop going through each one of the incident edges, right? So let's see what happens here. So first, before anything, are there any questions about how I modified Prim's algorithm here before I proceed? So remember, the big idea here is I'm just trying to eliminate having to go through all the vertices. Once I get through going through each time, selecting out the one that needs to go inside the blob, each vertex that has to go in the blob. Let me just make some space here. Let me make some space here. Give us some breathing room. There's a lot going on the board. So, if there aren't any questions about it, let's talk about the analysis here. So, the first parts are all the exact same. I already talked about the big O of n log n that occurs before I enter the while loop. Checking if a priority queue is empty takes constant time, right? So you know right away that's not really an issue here. Keep in mind I would make sure I account for this in my time complexity analysis when I write it out. But now I have remove min. You know that this takes big O of log n time, right? It takes big O of log n to do remove min. We talked about this earlier on in the course. I'm going to switch my marker to blue because that black is a little bit hard to tell between parts that I have there. And then next, marking, I can do that in constant time if I wanted to. So I'll just lump that in with the big O of log n. Many operations. I'm just doing this for the sake of time. And then I go through each one of the incident edges. Now, there's something else going on here we have to be a bit careful about, right? This decrease key. Remember, the decrease key, this does not take a constant number of operations. In fact, if you took everything I have right here, in terms of the number of operations, in the worst case, you're going to end up at where it's going to be, inside of this for each loop, you're going to have big O of log n operations, right? Because we said the decrease key takes big O of log n, many operations in the worst case, right? So it's a little bit different now. So you notice how I now pushed a lot more operations over to this loop now. It's a little subtle that I did that because now I have to count this a little bit more carefully. So back to the same exercise I did a moment ago. If I am wanting to consider an adjacency list, and I must stress you could go through the same exercise with an adjacency matrix. It's not nearly as interesting though. I will tell you that up front. If I go through the adjacency list, well, we know we have something that's big O. We have the first part that's big O of n. We got some stuff that's big O of n log n, right? And then we have we have something else going on here. We know that this log n is going to happen, this big O of log n is going to happen exactly n times, right? So we know that like this part of the while loop with this together, all of this together, this is big O of n log n many operations. You're going to see that I'm going to peel open the while loop and I'm going to count specific parts. So this is a little bit unusual from the kinds of counting that we've done in the past. So I'm going to rip open this while loop and I'm going to count parts of the code as frequency with the outermost while loop. So that part right there, we know that's big O of n log n, right? Because I go through each one of the vertices, I apply remove min, right? Now, what's happening with this for each loop in combination with the while loop? That's the part that's interesting. So, remember we established that the number of operations, if this was a constant number of operations that was happening here, we already said that, okay, the number of times this will happen in combination with the outermost loop, because I went through each one of the vertices, we said that that's big O of m, right? We said that earlier. Because you remember we used the handshaking lemma. We summed over all the degrees. So we know right away we're going to end up with something that's like big O of m with a something. Can somebody tell me how many operations are happening for this for each loop in combination with the while loop? What else needs to go right here? I'm missing something. What am I missing here? So it doesn't take a constant number of operations inside of each iteration there. Now it's big O of log n, right? So what should go right here? So we established that it's big O of m originally, but yeah, it's log n. Log n has got to go right here. Because remember, for each iteration where I go through each one of the incident edges, I perform big O of log n operations because of the decrease key operation. So, let's put this all together now. So I have n log n, and m log n. Now you might look at this very quickly and be like, okay, so you have n's and m's going on here. Now, the first thing you might tell me is, Dan, what are you doing with this? Well, I can tell you, I could take all of these functions. If I stripped off the big O's, I could just simply, notice I have an n log n and an m log n. I could tell you that if I summed over m and n together, that this most certainly would be m plus n log n. Right? This most certainly has to be the case that it's m plus n log n. But remember, the graph is connected. So if the graph is connected, I could actually simplify this down. So let's talk about that. So let's see here. So this is big O of m log n as G is connected. So remember, the minimum number of edges a connected graph has in relation to m, remember that's a tree, right? A tree would be the minimum number of edges that you would need to form a connected graph of n vertices, right? You would have one less edge than the number of vertices. Likewise, that means you can have more edges than that. So it's very easy for me to just simply drop the n and just put m here by itself. So this is because the graph is connected. If it was not connected, I would have to stay with this. Okay, so you'll notice that now this is m log n. It is not n squared anymore. So if the graph is sparse, as in it has very few edges, this is much better. In fact, if it was that m is big O of n, you have it where the running time will be something closer to big O of n log n, or big theta n log n, which is considerably better than n squared, right? So you have a couple choices here. So if you think about it, if you're doing an adjacency matrix where the graph is dense, you might want to use the array-based implementation I was describing earlier. if you have a sparse graph with very few edges in it, maybe use an adjacency list with this priority queue-based implementation. So do you see how, depending on the choices we make with the data structures and how we represent the graph, can actually influence heavily the time complexity of the algorithm? So very often when we develop or design the algorithms, we have to make these choices very carefully if we really want to speed up the data structures or speed up the algorithms that are a part of the entire whole of it. This is why very often when you learn data structures and algorithms together, people will tell you that there's a big role that both of them play when you're trying to solve a problem. And that's exactly the point I'm trying to make here. So are there any questions about this running time here that I've established? Before I have a couple last remarks about minimum spanning tree, before we start talking about single source shortest paths. So one thing, as you're thinking about that, one remark I want to make is that you could take this even further. You could take this to a whole other mile. Now, you might recall from the readings I gave you on mergeable heaps, there's something called a Fibonacci heap. And in a Fibonacci heap, you can actually you can use the exact same idea I have for the heap-based implementation. You can use that kind of heap instead, and you can actually achieve an even better running time. So one thing I will point out is that using a Fibonacci heap and an adjacency list, we have worst case time complexity. Big O of m plus n log n. So you'll notice that if I use a Fibonacci heap, this actually approaches much better what I was trying to ideally get, where I get like n log n. Notice now it's m plus n log n. So you can get the n log n, and you just sort of suffer the consequences of having to determine if the number of edges is many or not. So somebody had a question. The reason we dropped the first couple of terms is that they are insignificant as to compare the logarithmic terms, right? So it depends on what we're talking about here. If we're talking about up here, for example, if we're talking about the constant number of operations, we know that big O of 1 is a subset of big O of log n, for example. So if I give you some constant number of operations, most certainly those will be some set of operations that happen with respect to, if I count them, there's still going to be big O of log n, many of them. Even if it's a constant number of them, using the mayonnaise, the mustard, making an awesome sandwich, if I have a constant number of operations plus some other number of operations, and those are a logarithmic number, then it's still big O of a logarithmic function. But yeah, no, so the reason why I was able to I got rid of that one because n log n, because remember, n is big O of n log n, and so on. So all I'm doing is walking you through that process, and I'm just suppressing those details by using the convention of the equal sign, but remember, it's not an equal sign, it is, to suppress those details in my analysis. But I wanted to just mention that if you find yourself wanting to go beyond this, a Fibonacci heap will guarantee, in the worst case, m plus n log n. But yeah, so in the notes I included a little table, so if you want to see the trade-offs between representations versus what kind of implementation you want to use, it shows you the trade-offs between them. But anyways, that being said, are we okay with starting to talk about computing shortest paths, everybody? I'm really excited to show you this. Okay, so let's head over here. We're going to start talking about the single source shortest path problem. And I'm going to give you a quick breakdown of how I can solve this problem. And here's the cool part. I don't like using the word cool, but I think it's merited here, is that the algorithm I'm going to present you is nearly identical to Prim's algorithm. It just has a small change to it. Just a very small change to it. And it's just that the problems seem to be closely related to each other. So let's talk about the next problem. So let's talk about single source shortest path problem. So I promised I was going to show you how to compute a shortest path between two vertices. So I'm going to show you that a lot of the theory that we've talked about here can easily be adapted to solve this problem. In fact, many people will tell you, oh yeah, just if I showed you the algorithm that solves this problem, you can even look at Prim's algorithm as a special case of it, just in theory, but they're not really the same problem, just to be very clear. Just that the structure of these problems are very similar. So I need to define a couple quick things. So let G be a weighted undirected connected graph. I know it's a lot of descriptors. Undirected connected graph with non-negative edge weights. So one thing that you might find interesting is that you'll notice that whenever I talked about Prim's algorithm, I never ever brought up the idea that the edges could be negative, but Prim's actually works even when the edge weights are negative. There's nothing in the cut property that says that doesn't work or anything. For the problem that we're going to consider here, I need to presume that the edge weights are non-negative. So that's one thing I need to make an important remark about. So let G be a weighted undirected connected graph with non-negative edge weights. So I need to define the notion of a path again. So given a path, P is equal to, I'm going to give it as an ordered sequence of edges this time. So V0, V1, comma, V1, V2, all the way up to Vk minus 1, Vk. So this is what my path looks like. It's going to go V0 to V1, then goes V1 to V2, then it goes V2 to V3, then V3 to V4, and so on. The length, or total weight, or cost of the path is the sum all the edge weights in the path. Sometimes it'll be helpful for me to note this as W of P. So let me just write out what that is. So W of P is going to be equal to the sum over from I is equal to 0 to K minus 1. So it's K minus 1. K minus 1 of the weight of VI plus 1. So I'm just going through each one of the edges and I'm just getting its weight and I'm adding them up. That's all it is. So when I have this, I can define the notion of a shortest ST path for a weighted graph. So a path P from S to T with minimum weight of its path. So all I want to do is so what we're going to be doing is I want to try to find out how I can compute a path in a graph, such as I described up here. I want to compute a shortest ST path. So I want to compute a path P that goes from S to T with the smallest weight for its path, which intuitively you just simply say is the shortest distance to get from one vertex to another vertex where now the edge weights dictate the distances between the two vertices. So is that clear, everybody? And this is a very natural problem with numerous upon numerous of applications, whether it be routing. For example, you could imagine I could plot out a map. So you could have like a big map where you have a traffic where you want to go from one place to another place, but I want to do it in the shortest distance possible. That's a very natural way you could view this problem. So this is a classic combinatorial optimization problem, just like the minimum spanning tree problem is. And there's many algorithms for this problem. So the problem that we're going to be describing, I'm going to be highlighting one of them. There exists another classic algorithm for this problem. If I have time, I will highlight it. If not, I have a little description about it at the end of the notes. It has a couple neat features to it. But let's proceed. Let's proceed. So I got to give you a couple neat facts about computing shortest paths on a weighted graph. Now, if I had like a week to cover this topic, I would go through and prove each one of these with you. But instead, I'm just going to list out them as properties. But be aware that if I were to come along and I say this is a brand new problem that I just encountered, and I'm like, hey, look, I want to discover a new algorithm that solves this problem, or I want to design one. This discovery process oftentimes means studying the problem carefully and see if there's anything I can exploit to design the algorithm. So in this case, there's a couple really neat properties that shortest ST paths have in a weighted graph. So I'm going to list a couple useful properties, and the algorithm I'm going to describe to you actually uses them in a very clever way. So I'll just say a couple useful properties. So as I said, each one of these actually has a formal proof to it. But for the sake of our brevity, I'm going to omit those proofs here because their proofs are rather accessible online, and they're also rather, I think that they're not difficult to observe. So the first thing I want to point out, let me draw a picture here. I'm going to draw out a graph here. I'm just not going to bother about labels or anything on this graph. Let's make it look like this. I'm kind of drawing a fun doodle here, okay? So let's draw out this graph here. Here we go. So I'm going to label some weights on these edges. 3, 2, 6, 2, 2, 2, 5, 8, 3, 2, 2. And I'm going to make this vertex down here. I'm going to make that S. And I'm going to make this vertex over here T. I think I got all the edges. I think I've got them all. Okay. So I'm going to show you a couple neat properties that constitute shortest paths. So the first one that's rather neat is the following. So watch this. A subpath of a shortest path is also a shortest path. So you might say, Dan, what the heck does that mean? So it means if I gave you a shortest path, I can actually take any part of that shortest path, and if I look at that subpath, that will actually be a shortest path from whichever two vertices are the starts and the ends of that path. So wherever I begin and end, if it's a shortest path, whatever that little piece that I clip off is also has to be. So if you think about it for 1 second, well, what does that mean? So suppose that we tried to figure out what the shortest path is from S to T in this graph. So let's take a look here and let's see what we can do. So notice that I can't go this way up this way. So this might be a little bit too long, right? Because this will be 1 plus 6 plus 2. That's 9. So that's going to be too long. There might be a better one. Looks like I could take this one that goes up here, then goes there, right? We can go 3 plus 2, and that's 5. I think that's the best we can do here. I think that's the case. If anybody sees any better path, let me know. I think this is the best path I can get from S to T. So that's the shortest path, I believe. And it's this total weight or length of this path is 5. So what I'm saying is if I took this shortest path, and suppose I wanted the shortest path from this vertex to this vertex, it most certainly will be this one right here. Likewise, if I were to go from this vertex to this vertex, this is actually going to constitute a shortest path from this vertex to this vertex. That's what I'm saying. And you might ask, Dan, how do you know that that's true? Well, suppose otherwise. Think of it in terms of contradiction. So if I give you, suppose that I told you that there's an even shorter path or one with an equivalent length. What that would mean is I can simply find a different path that does not consist of this one. Well, what does that mean? What does that mean? That means that it has to have a shorter length or at least as long as mine, right? So I can easily take this new path and you say, okay, so I can go from there to there. Well, if it doesn't contain this edge here, the whole argument is it proceeds to the idea that there has to be some other path. And the idea is I'm going to show you can take and build a shorter path by actually introducing this edge and removing any edges that are actually going to end up making it longer by shortcutting it. But that's one way you can achieve this. There's a couple different ways you can prove this claim. One is through contradiction. That's one idea. Another one that I want to talk about. Sorry, I'm getting a little excited here. Another one, this is the one that I would consider the most important for the algorithm I'm going to show you here quickly, is there is a tree of shortest paths from a source or start vertex to every other vertex of G. This is called a shortest path tree of S. And I must stress that S is the root. Semicolon there. Every path from S to another vertex T in the tree is a shortest ST path. So it means that for any one case where you're trying to compute one of these ST paths, it's actually a part of a larger tree that actually contains a whole bunch of shortest ST paths. So if I consider this the source, so this is what I mean by a single source, is that the source is going to be something we talk about, and I want to find the shortest path from S to every other vertex. I can find out that if I give you two vertices, it's just simply one of the paths along this tree. So for example, this is, for example, a shortest ST path from this vertex to this vertex. This to here to there, that's a shortest ST path from this vertex to this vertex. Likewise, I can keep doing this. For example, if I were to do, I believe I got everything. I'm just trying to think if there's any shorter one. Yes! Oh, video's frozen. Is it frozen on your end? Okay. I just want... Okay. Oh no, that's not good. I'm hoping it's playing catch up here. On my side, it still looks okay, so I'm wondering if it's just Zoom just having a fart at the moment. My apologies, everybody. That's a new one for me. That's pretty epic. So let me just reiterate what I've done here. So anyways, you'll notice here if I look carefully at this tree that I've outlined in the blue lines, this actually constitutes, if I pick any two vertices in it, whatever path is there is in fact a shortest ST path. Okay, good. I don't know what happened there. That was really odd. But either way, I'm glad everybody's still here. It could have been way worse, right? We've already seen how that happens. Okay. So, anyways, what I would like to do, so I must stress that now I've shown you that there is such a thing as a shortest ST path, but there's this so-called shortest path tree, and the shortest path tree contains shortest paths. So a very natural way I can cast the shortest path problem that we're interested in is actually computing this tree here. So you might ask, okay, so what does that mean? So if I were to give you this tree, it's trivial to compute the shortest ST path if I give you two vertices, right? You would just simply pick whatever t is and you'd follow, for example, if I built a tree like I did for Prim's algorithm, you would just follow the parents back to S, just like when we did BFS, for example. In fact, you'll notice that this algorithm that I'm going to present you is a combination of this property with this formulation and breadth first search. So if you take those three pieces together, you get the algorithm we're going to talk about here in a moment. So I just want to first define the problem that we're looking at. It's called the single source shortest path problem. So what we're going to do is we're going to compute a shortest path tree, from S. And I must note that, remember, we're going to call S the source. So S, that's where this name comes from, S is called the source. So when I talk about the start vertex, that's the source. So likewise, you can define other shortest path problems, for example, where it is every possible pair of vertices. So in those cases, those are what we call all pairs shortest paths. In this case, we're just going to take one of the endpoints and we're going to say, hey, look, I want to find the shortest paths from myself to every other vertex. So I just want to bring up the construction of the algorithm. I know we only got a couple minutes here tops, so I want to just quickly run over the idea. And the cool part about this is that the algorithm is nearly identical to Prim's. There's actually only one small change in the algorithm. And once you see it, it's really simple. So let me bring up what this main idea is. So I told you that this is a lot like BFS, except we're going to incorporate something that we've seen in Prim's algorithm. So there's kind of two ideas. So we have two ideas. The first one is to use BFS so we can go level by level through the graph, akin to something like Prim's algorithm did. Kind of like Prim's algorithm did. And there's this other notion called an edge relaxation. So do you remember that when I told you these D values, right? The D values. Those D values were what I dictated to say, okay, the blob is going to devour that, right? Well, all we do to modify the algorithm I gave you earlier for Prim's is we're going to incorporate the edge relaxation. So wherever I did this update, where I picked the smallest of the least weight edges, now I'm going to imagine that the blob is really, really lazy. I mean, like so much lazier than we did in Prim's. So imagine the blob starts in one spot, say the source or start vertex, And what it does is it always picks at least, it's going to pick the next vertex or edge that takes it from inside the blob to outside the blob, but it always picks a vertex that is closest to the beginning or the source. So instead of it being where I just picked the one with the least weight edge, I'm now just going to pick the next vertex that's closest to where the blob started. So you can imagine it's like the blob just sitting there devouring the graph, but it's like, imagine this blob had a brain. It's just sitting there at the source, just hanging out there, but like, hey guys, I need to catch up, okay? Go over there. It's closest to me, okay? That's all the blob is going to do here. So the edge relaxation is going to be the same idea. It's going to be very similar to what we did in Prims, except you're going to have this condition, which I refer to as a edge relaxation. So relaxing an edge corresponds to this following check. So if u dot d plus the weight of the edges that I'm considering, so these would be your two endpoints, is less than v dot d, then you would just update the d value. U dot d plus the weight. So notice here, instead of it just being where I simply just go through and I just find the one with the smallest d value, now the d values are going to represent true distances. So now the d values are distances from the source to my vertex. So that's why I use the variable d, is because it represents the distance in this context. And if you take these two things together, you get Dijkstra's algorithm. You get Dijkstra's algorithm. And here's the cool part. The only change that's happening in the algorithm is the updates that happen associated with the d values and the parents. You just make this edge relaxation change, and you end up with Dijkstra's algorithm. That's how simple the change is. And with this, you can compute a shortest path tree. So just take a look at the pseudocode I have in the notes. So take a look at the pseudocode. And here's the other neat thing. Is since we know how Prim is analyzed, Dijkstra's is analyzed with the same time complexity because it does the same things with the exception of the edge relaxations that occur. So I want you to take a look at the pseudocode. So take a look at it and look at the example that's there of Dijkstra's algorithm. It seems like we ran out of time to talk about the example here. And I apologize for going a few more minutes than I intended here. So I'm going to let you go here. So I want you to take a look at the remainder of Dijkstra's algorithm. Please take a look at the algorithm. And remember, it's only that we made the blob lazier. It always will pick the vertex that is closest from the source vertex. That's what it does. It's just really lazy. So please take a look at the example, take a look at the pseudocode. And one thing I do want to make a remark about is that Dijkstra's algorithm will solve the single source shortest path problem as I defined it. But if you find yourself curious about other shortest path algorithms, there's another one called Bellman-Ford. I make some remarks about that in the notes at the very end. If you're curious about it, give it a read, okay? So we're going to stop right here. And when I come back, we're going to start talking about algorithm design techniques, okay? So that being said, I want to say thank you very much and have yourself a beautiful day. And I apologize again. So I'll see you later.